Okay, so greetings everyone. I am Devin Lloyd, fourth year industrial manufacturing engineering student, and I attend Florida A&M University. And this summer I did my research on the analysis of tape-to-tape contacts between Repco and cork wires. So cork stands for conductor on round core. And what that is a high temperature superconducting cable that's made up of multiple layers of Repco. And REPCO stands for rare earth or yttrium, barium copper oxide. And as you can see in the first image, you have an image of REPCO tapes being wound around a copper wire to produce what we call cork. The benefits of cork is that it allows current to be shared between conductors while minimizing the risk of burnout, which makes them great candidates for high field magnets, which are used in the MagLab and the Applied Superconductivity Center. So what we're going to be looking at in this presentation is the tape-to-tape contact resistance, and we're going to analyze how well uh, the tape-to-tape contact resistance determines how the current can be transferred during throughout these different cables. As you can see at the bottom, that image is similar to the type of cable that we were using during this research. It is a horseshoe single turn cork wire, and we're just going to take cross sections during the bend and during the straight areas of the wire to analyze the tape to tape contact resistance. So I mentioned superconductors. Superconductors are specialized materials that have zero resistance, and that's to ensure that no heat is generated while transferring electricity throughout the magnet. So the superconductor that we worked with are these Repco tapes. And in these Repco tapes, there's a thin black layer of Repco, as you can see in the first two images. And that is what carries the vast amount of electricity that's comparable to something like a large copper cable. The reason we're using these cables is because we can wind them into coils to be used for the superconducting magnets to create high magnetic fields. And we're doing this because sometimes the magnets operate under high stress and the cables might lose performance or even get damaged. So you're going to need alternative paths for current to go around degraded or damaged conductors. So the way we analyze these cables were first by cutting and polishing our samples. So we coated our cork wire and epoxy before cutting it, and then we cut it into about 1 centimeter samples before mounting them in pucks. After we mounted them in pucks, we polished them and went through the entire polishing process. And then for our imaging process, we used the optical microscope at 50 times zoom, where we went around the circumference of each of those cuts. And we took a program and measured the amount of contact that we saw between the Repco tapes and the amount of potential contact that we saw between the tapes, and then where there was no contact at all. So as you can see at the bottom, you have figure 1 and figure 2. Figure 1 shows where there's good areas of contact. The first two layers have good areas of contact, and then that last layer has what we would call potential contact. So we measured those and took the data. Figure 2 shows areas where in the first layer there's good contact, but in the last two layers there aren't quite good contact, and we wouldn't even label those potential contact. So those didn't get counted in our data. So this is just a graph of what we came up with percentage-wise as far as the amount of contact and potential contact that we found in each cut. As you can see on the right-hand side, that's a diagram of the cuts that we made on the wire. So the red line, it would be our wire. And then starting from the top would be our initial cut. And then we go 1 centimeter, 1 centimeter, 1 centimeter, which is what's shown on the graph. And our takeaways from this is that we saw evidence that cross sections in the bin have higher percentages of contact between tapes than cross sections that were cut from the end or the straight section of the wire. And this brings us closer to evidence that contact resistance is lower in the bin because contact overlap is higher. And furthermore, we saw through our images that as you progress down the wire, the contact between layers appeared less obvious to us. So that's why we have such large percentages of potential contact, because we weren't sure whether or not those tapes were actually touching each other or not. And that could have been because of the polishing process or other flaws, but more research is going to be done in the fall so that we can verify this evidence. I'd like to give a special thanks to Dr. Lance Cooley and Virginia Pfeiffer, as well as Leora Lewis, for helping me with this research. Thank you.